In this lecture, we're going to begin a discussion about sequential models, specifically Markov models or Markov chains, and we'll discuss the simplest case of a Markov model, which is a first-order Markov model. So let's begin the discussion on Markov chains. So here's a toy example. Often this example in textbooks is introduced with the story of a drunk walking down an alley. So we're going to modify it a little bit. And so let's imagine that we see a zombie walking in an alley. And each time it moves forward, it takes a step. But because it's staggering, it can move to the left. It'll take a step straight ahead, or it'll take a step to the right. And the probability of stepping left, straight, or right has probability PL, PS, or PR, except in the case where it's right up against the wall, in which case it's going to step straight with probability PSW, or it's going to take a step towards the middle of the street with probability PMW. So in this case, if we model the random walk in this case, we're also going to make the simplifying assumption that the distribution on the next location only depends on the current location. And so what we want to ultimately do is model the location in the street widthwise. So where is, not necessarily lengthwise, but where is this random walker in relation to the wall? And we're only going to assume that the next location is dependent on the current location. So let's simplify the problem by assuming that there are only a finite number of states. So if we wanted to measure the actual distance, for example, from the left wall as a function of time, that's going to be a continuous random variable. But we're going to discretize it and assume that there are only a finite number of states that this random zombie walker can be located in. In this case, we're going to add a latent variable, s, which gives the position as a function of time of the random walker. So for example, if at time t the walker is in state I, for example, this position 1 could be would be 1, 2, 3, or 4, etc. So let's discretize the state by the index of the position. So this would be the 20th position. And so now if we want to say what's the probability of the position at time t plus 1, or step t plus 1, given that at step t the position is I, and for simplicity in this slide, let's just assume that the walker is away from the wall. Then what this model would say is that the position at t plus 1, given that we're in position I at time t, is going to be equal to I plus 1 with probability of taking a step to the right. It's going to remain in position I with probability PS, which is the probability of taking a straight step. Or the position will be I minus 1 with probability PL, which is the probability of taking a step to the left. So this is a simple Markov chain. And because the distribution of the state at time t plus 1 or any time only depends on the position at the previous time, we say that this Markov chain has the first-order Markov property. So it would be a first-order Markov chain if my position at the next time point is only dependent on where I'm at currently. If my position in any given time is dependent on the previous two times, the previous two locations, that would be an example of a second-order Markov chain. Most of the time, when people are working with Markov chains, they're working with first-order Markov chains because the added complexity of working with higher orders is very difficult computationally. So most of the time, we'll make a first-order Markov chain if we're going to use a Markov model. Now we can put the transitions, these probabilities, into a matrix, and that's also a very common way to represent a Markov chain. So let's introduce this notation, the matrix M, which we're going to call Markov transition matrix, or a random walk matrix. There are a few names we can call it. And for simplicity, let's imagine that we have 6 different positions in this alley that this zombie is walking in. And these are called states. So every single position now is going to be called a state. That's a typical name for it. Then we can represent the transition matrix in this way. If we let the 6 positions be ordered based on where they are relative to the wall, so this would be the position next to the left wall, this would be the position next to the right wall, and these would be all the positions, the 4 positions in between. We would have a Markov transition matrix that looks like this. Given that I'm at one position, for example, the 3rd position, I go to the 1st position with the probability of walking to the left. I stay at the 3rd position with the probability of walking to the right, walking straight, or I go to the right position with the probability of walking to the right. And based on this simple modeling assumption that we're making for this toy problem, there's no probability of skipping other steps. So for this specific Markov chain, if we're in the 3rd position, we have 0 probability of moving to the 1st or the 5th or 6th positions. And so we get something like this. We can represent this random walk matrix, this random walking zombie, or drunk if you will, with this sort of a matrix if there are 6 different positions. And of course we can permute the rows and the columns as long as we know how to map back to a position. So if we want to say the 3rd state is equal to the location next to the right wall, we can do that. We just have to have a coherent, correct way of permuting these probabilities so that they relate to reality. Okay, but now we're still working within a toy example, and in reality we aren't necessarily going to know these things.